is, and I forgot to bring the flyers with me, but Math and Computer Science Picnic, Wednesday next week, 6:30, on the mall, kind of close to the chapel. We're gonna have food and sodas and stuff, and it'll be a lot of fun. So you should all come, and we'll be grilling and that sort of thing. So, um, yeah, this is the first time we've done one in the evening, but we're hoping that because things are busy at lunchtime, and especially those of you who are in fraternities that have to go back to the house for lunch and whatnot. But it also means Maryland, y'all can come and join us. So, and where's Arthur? Oh, well. So actually, this raises an interesting question. What happens if one of you skips class? Like, do I get to call the high school and get you in big trouble, or is he technically being a truant right now? He's breaking the law. Yeah. What do you guys think? Okay. Oh, well. We're just discussing whether or not it constitutes a crime if you two skip class. Kind of, yeah. So anyway, uh, you need to fix your collar, bro. Other side. Yeah. Okay. We'll have to teach you about collar stays someday. All right. So I wanted to start actually with a quick discussion of this whole buffer flushing thing. Um, and in particular, I wanted to show you guys what Drake did because this is a trick that he learned from Dr. McCartan Lim, and it's not something I had known about, so I thought I would just show it to you. Um, Once it loads, maybe. Here we go. So here's this function, void flush, and let me expand it a little bit. Um, and so it's just basically a while loop that waits until the get car buffer is sort of it scans through it until it's done scanning through it, and then there's nothing left in the buffer. So anyway, so this I think is a slightly more elegant solution to the whole input problem that a number of us had with assignment 3. So yeah, and I take it that ML just gave you guys this and said, oh, by the way, this is handy. So okay. Um, yeah, so anyway, I'll post that snippet up to Canvas because that, is kind of handy to know. That input stuff is always annoying. So c'est la vie. Um, Okay, so that was just a quick thing. And what I want to start on today is actually to start to look at assembly. Okay, let me close this, and I guess I can close. Well, actually, let me go back to home here. So, um, the architecture. Okay, if you go to here, this document. Let me just download a copy. Okay, it is a very, very, very large PDF file. Um, and this has basically almost everything that you could probably need to know about the ARM architecture. And it's, like a several thousand page PDF, just to keep things fun. Let's see what it says here once it finishes loading. Yeah, 2,856. And where's Noah? Mm, let the texting begin. If anybody has Noah's phone number, begin texting. I didn't. Oh, wait. No, I don't see it. Yeah. So, yeah, he's not here. Okay. Yeah, pretty much anything you could possibly need to know about the architecture is in here, including basically a listing of almost every instruction, and there are lots and lots of them, which is, um, you know, uh, lots and lots and lots. Okay. Um, and we'll talk through some of the basics to these. So for example, the add command. So the general idea behind the way um, a really any computer works is it fundamentally comes down to a cycle of fetching instructions, decoding instructions, executing instructions, and then this loop continues basically forever until the program terminates in some sort of way. So in memory, your program gets loaded in, and it's just a chunk of binary stuff, right? And then well, here, let me go into GDB because that'll make it a little bit more obvious. So let's go to, let's see, uh, what were we doing last time? Structs 2. Um, well, let me just make sure that I compile it. Um, oh, speaking of compiling, there was one other flag that you needed for in order for the square root and the power thing to work on assignment 4. I'll go ahead and use it here even though it's not necessary. So the flag, what was it, LM? Yeah. So lowercase l, lowercase m, you'll need that on number 4 for the power function and the square root thing to work correctly. But otherwise, so you need math.h and you need this extra flag. Um, for it to work. For this it won't matter because there's no math in this particular program, but whatever. Now this will actually not be a problem when we get into doing this with assembly because so um, the ARM architecture and really any computer architecture since the late 90s has had hardware square root instructions. Uh, so we don't have to rely on software square root stuff from the C standard library like you would have back in the mid or early 90s. And so because of this, when we do something involving a square root in assembly, it's going to be a non-issue. We'll just use the square root instruction and that'll be the end of it. But anyway, okay, so if we go into GDB, right, and I'm gonna just break here at main, okay, so that I'm breaking on line 1, and if I list, there's my program, okay, in terms of its um, uh, the well, okay, I clearly didn't put in the not much of a program because what's it going to do? Oh, okay, sorry, it only listed 10 lines. Okay, so my bad. Let's do, oops. Okay, so okay, so anyway, there's our code, right? We declared a string and we did some other stuff and okay, whatever. But if we look at the registers, okay, so each, there are 32 uh, general purpose registers. Some of them have specialized uses. And so let me hit enter and go to this one. So the specialized ones are down here at the bottom, okay? There's X30 and X29 have special purposes, and we'll talk about what those are later, okay? And then, why did my mouse die? I think this may have just crashed. Yep, it just hard crashed, I think. Yeah. Oh, no, wait, there we go. All right, let me just close it and restart it because something's messed up. Yeah, the 9,000 page PDF being open probably has made it unhappy, but that's okay. We don't need the 9,000 page PDF right now, so, or Canvas for that matter. Okay, so where were we? Oops. Oh, yeah, hold on. Let me actually recompile it real quick. We also need for the static flag, and we'll talk about what that is later. Okay, so I just executed an instruction we've stepped through, and then I want to look at the registers. Okay, so there are, like I said, 32 of these things, although really for your purposes, there's only 29 that you want to be using. And so in the specialized one here, the first one that's important is PC or program counter. Okay, so this is when your program starts, the program counter is a pointer to an address in memory where the next instruction is to be loaded from. Okay, so the program part of your program, as opposed to the data part that's got like the string and crap like that, is just a big list of instructions, right? And they're all in memory addresses. And you start your program at whatever the base memory address is. Okay, now that you don't necessarily get to determine, the OS or whatever will. And so in this particular case, our program started at 48 bytes previous to this number, okay? And the program counter is going to go through the instructions, and on this particular architecture, every instruction is 32 bits, period, okay? And so what that means is that the program counter is going to be incrementing by 4 bytes at a time to load in each next instruction, okay? So whatever the base address of the first instruction is, that thing gets loaded in, whatever that instruction is, it gets decoded, and then it gets executed. Now, when I say instruction, I mean quite a bit more nitty-gritty than what we do in C, right? So what might be a single line in C could end up being like several lines worth of assembly. Okay, so this is one reason that C is really nice, is that you don't have to think about it quite that low level, but that ship is about to sail. Okay, then there are status registers. Okay, the processor status register, which contains a bunch of single bit flags that tell you certain things. So for example, was there a carry on the last arithmetic instruction, right? So if you do addition of two numbers, there might have been an overflow into 33rd or 65th bit, did that occur or not? Okay. Huh? The carry flag. Okay. And there are versions of instructions that either do or do not take into account the carry flag. The Z flag is for 0. Okay. So if you do an arithmetic operation, like let's say you subtract one number from another and the result is 0, then the carry flag, or sorry, the 0 flag is going to get set. And then you can use that as the basis for like an if-then kind of statement. Okay. And then there's other flags too, which we don't have to talk about right now. But the carry, the 0, the negative, the uh, overflow, some of those are going to be kind of useful. Okay. There are sort of some floating point registers, which we can just ignore for now. And then X29 and X30 are the special ones because those have a dedicated use. And that's sort of a Linux thing to make those particular ones the special ones. X30 is called the link register. And basically, if you have a program that transfers from one function to another, you have to kind of keep a breadcrumb trail as to where you came from, and the link register is sort of the breadcrumb that's right in front of you. Okay. X29 is this thing called the frame pointer. We'll talk about that later. The stack pointer technically is X31, but we'll just call it the stack pointer. Basically, that points to a location in memory where your program has access to data or to store data. Okay, so whenever you're like transferring into a function and you have local variables or something like that, those things are going to end up in the stack in some way, shape, or form. Okay, and you'll notice that in this case, the stack address is very, very different from the program counter address, which means the code part of our program is in one chunk of memory, and the data part of our program is in a completely different chunk of memory, and the OS is going to kind of manage where that is. For our purposes, we don't really care numerically where it is, it's just somewhere in memory. Okay. Okay. So now the rest of these registers, you can basically use them for whatever you want, but there's some restrictions that are placed on it by the conventions within Linux and whatnot, that if you want to pass parameters to functions, you use the first 8 registers. The next chunk you use for sort of temporary computations. But for most purposes, you really never need more than the first 5 or 6 in practice. But if you want to get really tightly optimized, you could use a bunch more. So most of these, we don't necessarily need to use, but we'll see when it's sort of appropriate to use them as we go. So the registers on this machine, it's a 64-bit machine, and so what that means is the width, well, 2 things. The width of the registers are 64-bit, and the width of the address space is 64 bits. Okay. Back in the day, though, those 2 things weren't necessarily the same. So in like say early Intel stuff, the registers were 16-bit, even though the address space was only 8-bit or whatever. Okay, and so it was saying 64-bit didn't necessarily mean what you thought it meant. If you want to put in a 32-bit number, then you call these register W0 or whatever instead of X0. And so the distinction here is that the W part is the first 32 bits of an X. And so it sits inside of it. Okay, so like if I just sort of sketch it here on the board, right, we'd have 32 bits in a W0, and then that whole thing sits inside X0. So W0 is not a separate physical thing from X0. It's just the first 32 bits of it. Okay. Similarly, this will be the case for some of the floating point stuff when we talk about that. There's an entirely separate set of floating point registers that we call either S or D, depending on whether it's single or double precision floats, so 32 or 64 bit. But they're kind of oriented the same way, that the 32 bit part is really within the 64 bit part. They're not physically separate. Okay, so that can cause you some trouble if you're trying to load something into W0 and X0. Well, they're really the same place, so you can't use it in two ways. Okay. So does this fetch, decode, execute thing kind of make sense? It's going to read through memory. Yeah, Drake. No, this is the contents of the registers. Okay, and displayed here in hex, and then of course decimal, or well, as an integer. The assembly. So let's actually quit and redo this. So let's do GCC-S and open the actual assembly file for this. Hmm. No, you will be writing native assembly. Well, okay. If you have C code and you want to look at what the assembly is for that C code, yeah, you use GCC. Okay, but basically after today, you won't be really touching GCC, with one minor exception, which I'll talk about. So if we open the assembly for it, it's this, okay? And there's a bunch of sort of stuff up at the top that tells the assembler how to do some certain things. A lot of these things, particularly these aligns, you don't actually have to put in. We'll see that in a second. And then there's a bunch of this other kind of stuff that we can ignore. But the very first instruction that actually happens in our program is this one. Okay, and so X29 and X30 are special registers, and you have to save your trail of breadcrumbs, so to speak, in order to follow the trail of breadcrumbs back to where you started. Okay, so if um, uh, if you're like, well, let's take for example what are the things we did here, right? We were printing a string. Okay, so our program called another program in order to handle the actual printing part. Okay, and that program has its own code and it's doing its own stuff. Okay, so what we have to do anytime we have a program or a subroutine or whatever is the very first thing we need to do is we need to save our breadcrumb trail basically to memory so that when we hand off control to another program, it will save the breadcrumb trail to memory, and then it knows how to get back to where it came from, which was us. Okay, and so basically, the very first instruction for almost probably every program that we write will be some variation of the one that I've highlighted there, which is called the store pair instruction. Okay, and what this does is it takes the contents of two registers and transfers both of them to memory at a location of your choosing. And in this case, the location is chosen relative to the stack pointer, and this minus 80 means that it's going to allocate, it's going to take the stack pointer, subtract 80 bytes from it. Oops. It means nobody's moving because the sensor's over here and it has to detect movement. So anyway, I should put a bunch of mirrors up in front of it so that it gets detects movement from all over. Um, anyway, where was I before I was so rudely interrupted? The stack stuff, right? So what it's going to do there is basically allocate that 80 means 80 bytes, okay? And it's going to expand the data stack by 80 bytes and then take these two registers, the X29 and X30, and put them at the on the stack. And then the reason it's 80 bytes, which may seem like way too much, is because it's basically allocating enough other memory for some of the other things that we're going to need, like, uh, you know, hello world and where are we going to load this stuff into and so on. Okay. And then at the very end, you'll notice there's also the, the sort of symmetric inverse of that instruction, which takes things back off the stack, puts them back into memory or into the registers, and then sort of pops the stack, if you will. Um, so you can think of the stack as um, like, well, I don't know if this analogy is really going to make much sense. But has anybody worked in like a cafeteria or whatever where there's like a big stack of plates, or maybe in the fraternities, and it's like there's a big circular hole and there's like a spring-loaded thing, and as you put the plates on, they sort of sink into this cavity, right? And as you push them down, right, the stack kind of works like that, okay? In the sense that you're pushing a plate onto the stack and then you pull one off. Yeah. So yeah, good question. What's 29 and 30? Well, 29 and 30 are your frame pointer, which is relates to stack memory management, and your link register, respectively. So X30 is the super important one because that's the one where um, where your sort of last breadcrumb sits. Okay, and then so if you're to follow the breadcrumb trail, what you basically do is pop the value off of the breadcrumb trail on the stack, and the closest breadcrumb to you goes into X30. And then you'd come back up another breadcrumb, and then you'd do it again and do it again, right? So that will become, I think, excuse me, a little bit more clear when we look at recursion, okay? Because the stack will kind of we'll get a big stack of plates and then we'll go back to having no plates. Okay. Um, and yeah. Okay. Um, so that's what those registers are, even though they're just called X29 and X30. Now, some of that is there's no reason that, like, why did it have to be X29 and X30? Why wasn't it 0 and 1? Well, that's kind of an arbitrary decision to some extent, right? So some of this is sort of Linux convention, and some of it is ARM architecture convention. So does anybody actually have an M1 Mac? No? Okay. I've been wanting to get my hands on one because it's an ARM Mac desktop. Well, not an iPad or something. And I'm kind of curious as to if we were to assemble this on an ARM Mac, what, if anything, would look different about the assembly. So a lot of it would be the same, but there might be a few differences in terms of like which registers are used for what. And I actually don't know. So anyway, um, okay. And so you notice here though that what was a 26 line program in C is how many lines in here? Yeah, a lot, right? But point being, it's a lot more than 26, right? Um, each instruction of C does not necessarily correspond to a single assembly instruction. It might be multiple of them. And the job of a compiler is to make you not have to worry about this, right? It just all magically happens and you don't have to think about uh, any of this memory management or whatever. Okay, so let's look at what was the second to last instruction, or sorry, the last instruction in basically all of our C programs. Return 0, okay? And that, there are two commands that do that. The first one is that we have to load the number 0 into a register. And then the ret is the return, okay? So the convention here is that you pass parameters to and fro using the X and W and, well, using your registers, okay? But in particular, the first 7 of them. And if you need more than that, then you have to use the stack. And, okay, in the case where I typed return 0, okay, what did the compiler assume that 0 meant? That it was 0 as an integer, right? A 32-bit integer. Okay, and that's why it's moved into W0, not X0, because I'm loading 0 as a 32-bit number, not as a 64-bit number. Okay, and then why is this command move? Well, it just is. Okay, so, and this is one of the things that will probably drive you crazy, the difference between moving and loading. Okay, but maybe the best way to say it, at least on this architecture, is you load from memory to a register, okay? You move either register to register or an immediate value to a register, okay? So in this case, 0 is what we call an immediate value because it's specified what that number is. It's not a number that's a mystery that's sitting out in memory or something. It's a number that we've chosen in advance. And in this case, we chose it because, well, 0 is the exit status normal thing in Linux. Okay, so, right, so even that simple return 0 instruction was not, in fact, a single instruction in the assembly. Okay, all right, so let's start a brand new file and do some Hello World stuff. Okay, so, oh, that's very annoying. Oh, that is most annoying. My reference, for some reason, only has 1 page in it, but whatever. Okay. Okay, that's not what I wanted. Okay, this will work. Okay, so let's just start a new file here. I'm going to save this as, so let's go to our examples folder, make a new folder. Okay, and all right, so the convention I like to use, although everybody doesn't necessarily follow this, is if I am handwriting assembly, I use .asm as the file extension. If I am using machine produced assembly, like from the compiler or something, I use .s as the extension. And the reason that I do that is because then it's very obvious which files are machine produced and which files are hand produced. And I don't accidentally overwrite my own stuff. Okay, so so if you stick with that convention, I think that'll keep your life life happy. Okay, so there are several sections um, to an assembly file. Okay, you have data, you have text, and the program stuff actually goes in the text section. The data section would be where we could put like strings or numbers or other things of that sort. Okay, so for example, in our case, okay, I can define a string called hello string, whatever, and it is an ASCII encoded thing. And I don't know why you put a Z at the end, it just looks cool. And then there's our string, okay? And we can still use certain C functions. So one of the things that we'll sort of do is we can mix and use some parts of C and do other parts in assembly. We don't have to. I'll show you guys a different way to do it later, where we sort of rely on the OS's services rather than the C standard library. Okay, but I could define here however many strings I wanted. Okay, and maybe other data, so numerical data or something of that sort. Okay, and then you need basically a routine. Okay, and if you want to mix C with assembly, or things from the C library with assembly, GCC is kind of, we'll still have to use GCC, even though we won't really be compiling with it. GCC is kind of picky in the sense that there must be a function called main, okay? And if you don't call it main for the sort of outermost function, it gets really ornery. Does it really have to be that way? No, but whatever, okay? So what this is, when you put a colon, it's a label, okay? And then below that, I will have a bunch of instructions that go with this. And you can sort of think about that as like when I have in C, you know, int main void, or and then a bunch of stuff in curly braces. The stuff in curly braces is what goes with the main routine. So any instructions that go with main, I'll put below it, and then I can have another label to another set of instructions, and we'll look at that later as we make these more exotic. Okay, so the first instruction I'm going to have is that. And then the last instructions I'm going to have are okay, are these. So, oh, and one other. Okay, so basically this will always be our first and last instructions. Okay, load or store pair, basically the program started, let's take the current value of the link register and the frame pointer, pop them or push them onto the stack, and then at the end we pop it and go back to return control to the OS. So what happens when you hit this ret command is basically the link register, which is the last breadcrumb, okay, gets loaded into the program counter. And so if the OS gave, you know, handed over control to this program, where the OS's code was immediately before it transferred control is what's in that link register. And so the ret puts that back into the program counter. The program counter then goes over to that other segment of memory, wherever the OS's code was, and then continues executing the operating system's code. Okay, so that's how you transfer control from one program or subroutine to another. Okay, so we'll look at that in a little bit. Okay, and so let's just do some printing here. What did you need in what did you need in oh, hang on one second. What did you need to print a string in C? Okay, so we used the function printf. Okay, there are other functions for this, but that's the one we used. Okay, you need a format string of some sort. Okay, now unless, right, you only needed a format string if you were, well, like, so could I have done printf quote hello world? Yeah, okay. And so what do I need to tell printf to actually complete that task? What got passed? A pointer to, excuse me, the string, and possibly more stuff, right? So like if I wanted to print a number, what did I have to do? I had to have a format string and the number that I wanted to be printed, okay? But if I just want to print a string, okay, what do I need? I need the address to that format string, to the string, okay? And do I need to pass anything else to printf? Is it required to anyway? No, okay. Maybe it would have been useful to pass the length of the string to printf or something like that, but as we've seen, do we really need to know the length of the string to do stuff with it? No, because we can always just start printing characters until we hit a null terminator and then we know we're done, right? Okay, so if we're to call printf here, what we need to do is we need to load the address of that format string, or our string in this case. That address has got to be passed to the function, okay? Now, what's the convention here about passing parameters? In C, what did we do? Printf, parentheses, and then we put the name of the string, which was really the pointer to the string, okay? And so you just said, oh, well, I just passed the pointer, great. Okay, but really what did I do? Parameters get passed in the first 8 registers, so x0 through x7, okay? And they're going to be x's here for the most part because a pointer is how big? 64 bits, okay? And so what I need to do is I need to figure out, okay, my hello string is sitting in memory somewhere, okay? Now, I don't know where that is yet, but wherever it is, sort of the pointer to it, is the thing I need to pass to printf. Okay. The other convention is that, let's say that you had 5 things that you wanted to pass to printf, and they were in order, sort of thing 1, thing 2, thing 3, thing 4, thing 5. Okay, those go in the same order of the registers. So if you were passing, say, for example, 5 pointers, it would be x0 for the first one, x1 for the second, x2 for the third, and so on, and they stay in the same order, okay? Now, in our case, how many things do we need to pass to printf? Just one thing, okay? And so that will go in x0, and that's the end of it, okay? And what's going to go in x0 is the address of the format string, okay? Which the way we do this in assembly, or one way to do it anyway, is you just put an equals in front of it, okay? So hello dash str is my string, and equals that is the pointer to it. okay? And then I'm going to take, so this is a memory address, and I'm going to load it into X0, okay? And we'll step through these instructions one at a time in GDB, and I think it'll become a little bit more clear what's happening, okay? Then I need to transfer control to the printf function so it can do its thing, okay? And the way I do that is the instruction is BL, and that stands for branch and link, okay? So what that does is when we hit that line, our program counter's value is something. When you branch and link, what you do is you say, okay, I'm going to take my current value of the program counter and move it to the link register, and then change the program counter to wherever printf is in memory. Printf is going to then do its thing, and at the very end, when printf hits its RET command, it's going to pop the link register back into the program counter, and we would come back to one line further down. Okay, so yeah, is that okay? Maybe it'll start to sink in, don't worry. Okay, so we'll print the thing, and then that's it. We're done. Okay, for this particular program. Yeah. Sort of. Okay, so yeah, why 16 here? At minimum, it has to be 16 because I'm storing 64 bits worth of, or well, actually 2 copies of 64-bit things, right? Um, and so that's a number of bytes, not bits. Uh, and how much data have I needed to push on the stack? In this case, only uh, 16 bytes worth of stuff, okay? Now, I could make that number bigger and allocate more space on the stack. But as you'll see, we have to be a little careful because we have to make sure that anytime we expand the stack, somewhere later in the program, we symmetrically shrink the stack, okay? And if we're not careful about that, then what can happen is either the stack will grow too big, or, well, too big is not really the right point, right way of putting it, but so think about the stack this way. Let's go back to our stack of plates example, okay? When your program starts, there are no plates, okay, in the little thingy. And you're going to be putting plates in, and you're going to be popping plates out. And when you're done with your program, there should be no plates, okay? And so if whenever you push a set of plates onto the stack, later in the program, there has to be the symmetric amount coming back off the stack, or else you'll end up in the situation where there are plates left over, or, and this is where the analogy breaks down, you have negative plates in your stack, okay? So if you screw that up, then what's gonna happen is you're gonna start to access memory that you're not supposed to, and you're gonna lose track of your breadcrumb trail. And then your program is gonna either segfault or throw some other error, okay? And so maybe the best way to do this is to only expand the stack by however much you need right at that moment. And then if you need more data later, we can expand it later. Now, could we then optimize that after thinking? Yes, but we have to be very careful about memory management. Okay, and this is something that you don't have to worry about in C, right? You just do it, and the compiler just magically does it, and you're happy, and life is good. Where's Caleb? Oh, I don't know. I think Caleb should be fined many gentlemen's coin. What do you guys think? That power? And that's him? Yeah. Let's see if I've got a message on Discord. No. That would make sense. He must be asleep. Um, yeah. So anyway, okay. So there's our program. All right. Now, how do we actually run this thing? Okay, because there's several steps that we need to go through first. On the very first assignment, I kind of had you guys do it the full sequence, right? So I had you GCC to produce assembly, assemble to produce object code, and then link with GCC. Okay, we're still going to use GCC for linking anytime we use something like printf or scanf or any of the C functions. We could use Linux built-in stuff, and like I said, I'll show you some of those later. But for now, we'll just do this. Okay, so how do I run this thing? Well, let's go back to the directory, okay, and I've got this. So step one is to assemble it, okay? And in fact, let me throw in the debugging flag here. Crap. Hold on. What am I doing wrong? All right, hang on. That's in the data section. ASCIZ, hello world. Okay, why is this complaining? I don't think this matters, but oh, okay, it just didn't like the dash. I'm not sure why that is, but whatever. Okay. Um, so yes, it did not like the dash. Okay, fine, great. So I've assembled it. Okay, and oops. Okay, hold on. Let me find what the syntax for this was. Um, well, okay, we don't need to worry about that. So let me do GCC-G